Well, let's look another one. And this equation, we have a overly determined system. The previous one I called it underdetermined because you have 3 variables, only 2 equations in reality. And this one you have 3 variables but 4 equations. Well, if you carefully check the first 3 equations, that equation is precisely what we solved here. I just want to make my life easy to let you know, oh, this overdetermined system, if I select the first 3, I can solve it. And what's the solution? It's going to be 0, 0, 2. So x1 equals 0, x2 equals 0, x3 equals 2. Now, if you plug into the 4th equation, 0, 0, 2, well, you find the trouble. The left hand is 2, the right hand is 2.1. That's a contradiction. 2 never equal 2.1. Doesn't matter what x, y, z you get. So theoretically, we say no solution. You're done. But practically, all this algebraic equation may come from your measurement. And all your measurement have some measurement error. So you cannot be precise. So it's very possible you do over measurement to make it more precise. Then you get more equation than the variables. And then you are not looking for the precise solution. You're looking for a solution make the minimum error. That will be a topic for the next module. We're going to stop here. In summary, if you have an overly determined system, you have more equations than the variables. To this last equation, there's only 2 possibilities. Either this equation are exactly conform to the previous 3 equations. Then I call it redundant. Basically, redundant means useless, no more information. Or, like what we had here for this example, you got a contradiction. Then you say, this system have no solution. I would like to summarize these 3 examples by looking the geometric interpretation. Let's focus in 3D with 3 variables. In 3D with 3 variables x, y, z, you can think x is stand for the north direction, y for east direction, and z for the upward direction. So if I give you an equation, you may remember we can write a plane into a point normal equation. In other words, pass one point perpendicular to a particular direction, you get a unique plane. This plane, if you rewrite it, it will be like a standard equation. You just remove all these 3 constants to the right hand. So what I'm saying is one equation corresponds to a plane in geometry. 3 equations will map into 3 planes in the space. To solve the system equation, you really try to find the common point in all three planes. Well, this common point may or may not exist. Depends on the orientation and the position of the three planes. The three planes. So in our first example, you have a unique solution, means the three planes intersect exactly one common point. The second equation, the three planes really all intersect by one straight line. Then basically you only have two independent planes that intersect into a straight line. The third example, you have four planes. Four planes, most of the time, they're not going to have any common points to share. So that all makes sense now. The last thing I want to point out is the right hand, this D. If I give you an equation like x plus y plus z equal 5, another one x plus y plus z equal 10, this 5 and 10 simply tell you the distance between the plane to the origin are different. So the distance from the first plane to the origin is only half to the second plane to the origin. The formula precise the distance to the origin is the right hand divided by the square root of the a squared plus b squared plus c squared actually is the length of the normal vector. So in our case, the first example have a distance equals 5 divided by square root of 3. Second one is 10 divided by square root of 3. So that d stands from the distance to the origin. If the normal vector is a unit vector, if the length is 1, then the d is the precise distance to the origin. One more example. What about the d equals 0? If that equals 0, simply tell you the plane past the origin. Notice the distance to the origin is 0. And that's all you need to remember for the next topics. So the next few examples, we're going to consider a special type of system. We make all the constant on the right hand equal 0. When all the constant in the right hand equals 0, we give a name. We call it a homogeneous systems. Homogeneous, in a sense, all x, y, z on the left hand are constant, the first degree, and the right hand are all zeros. So just to show you one example. Now this is a homogeneous system. See the right hand, all 3 zeros. Well, when we consider homogeneous system, you just think, if we put zeros for every variable, so 0 times anything is 0, that is very clear. You get a solution, which is 0, 0, 0. Because when you plug in 0 on the left hand, every single equation left is 0, and 0 equals 0, this perfectly solves the equation. If you look at the geometric meaning, that's more illustrative. All the planes pass the origin. If all 3 planes pass the origin, and this origin 0, 0, 0, obviously is a solution. So if that's all, nothing to talk about, nothing interesting. So we look at the different situations. We start to look at the determinant. We know the determinant determine if the inverse of the matrix exists or the inverse does not exist. Let's assume the determinant is not equal 0. If the determinant not equal 0, then the inverse exists. And to solve this equation, the inverse exists, then you multiply the inverse on both sides. And then on the right side, because they're all 0, you multiply the inverse to 0. 0 times anything is 0. And the only solution you get is 0. If you know you have the 0 solution and the only 0 solution, you're done. No more questions. Nothing interesting we're going to discuss about it. So I'm saying if it's non-singular, inverse exists, there's nothing to talk about it, the homogeneous system, because the only thing you get is 0. What we are concerning is when this determinant is not 0, when this A inverse does not exist. And then we're going to look for non-zero solution. Those 0 solution, we give a name called the trivial solution. Trivial means not interesting. What we are looking for is the situation singular A and the non-trivial, or say no-zero solution, non-trivial solutions. That's what I'm looking for. Let's start from an example.